Okay, so let's see, what does this problem say? The accompanying figure shows a single turn rectangular coil that has a resistance of 2 ohms. The magnetic field at all points inside the coil varies according to B equal to B naught e to the power minus alpha t, where B naught is 0.25 Tesla and alpha is 200 Hertz. What is the current induced in the coil at t equal to at 1 millisecond, 2 milliseconds, and 2 seconds? All right. So let's find the EMF induced. Faraday's law tells us the EMF induced is minus d phi by dt, and the negative sign is that tells you is related to the direction of the current flow. Okay, well we will come to that, but right now all we want is the magnitude of the EMF. So magnitude of the EMF is that's equal to minus d by dt of B times A. The magnetic field is perpendicular to the plane of the loop, and so the flux is B times A. The area of the loop is fixed, of course, so the EMF induced is area times dB by dt. Okay, and area times d by dt of B naught e to the power minus alpha t equal to A alpha B naught e to the power minus alpha t. That's the induced EMF. And what is it that they want inside the coil? What is the current induced? Okay, so the current is, of course, EMF divided by the resistance, so it's A alpha B naught R e to the power of minus alpha t. Okay, now we're ready to calculate the current at various times, and I'll just do, okay, what I'll first do is calculate this factor first, and then it's just a matter of putting in different times. So let's calculate that factor. This factor, A alpha B naught R, is equal to A is the area of the loop, which is 2 times 5, 10 centimeter cube, 10 centimeter square, and we'll convert that to meter square. Alpha is 200 Hertz, 200, 1 over seconds. B naught is 0.25 Tesla, and oops, let me fix this. So area is 10 into 10 minus 4 meter square. Alpha is 200 and B naught is 0.25 Tesla divided by R, which is 2 ohms. And this works out to and oops, and this will work out to, well, this is current, so the units should work out to amps. Okay, so let's take care of powers of 10. The 2 cancel, that gives you 100. 100 times 10 is 1000, and that's 10 minus 1, so this gives you, and 10 minus 1 times 0.25 is 0.025. 0.025 amps equal to 25 milliamps. So that's what this factor is. Okay. Now let's add a page. Okay, so now we'll find current at various times. So okay, so we will write the expression for the current as current at time 0 e to the power of minus alpha t, where we just found I0, of course, is A alpha B naught divided by R, which we found to be 25 milliamps. Okay, so I at for A t is 0.1 millisecond, so 0.001 second equal to 25 milliamps times e to the power of minus 200 into 200 hertz, 0.001 second. Okay, of course the exponent has to be dimensionless, and it is dimensionless. Oops, let me fix this. 200 1 over second, 0.001 second. So this is equal to 25 milliamps times e to the power minus 0.2, and that is equal to so this works out to 20.5 milliamps. So I at 1 millisecond, the current at 1 millisecond is 20.5 milliamps. Okay. Similarly, you can do at 2 milliseconds, and I won't do that. You guys can do that. I will do part C, which is you'll see so part C, the current at t equal to 2 seconds. 2 seconds is essentially infinity. So you'll see that in a second. I 2 seconds equal to 25 milliamps times e to the power of minus 200, 1 over second, 2 seconds. So this is 25 milliamps. And you notice that at t equal to infinity, the current goes to 0. Okay, so this is, and you'll see that 2 seconds is essentially going to be a long time. E to the power of minus 400, and your calculator probably won't even be able to evaluate e to the minus 400. Okay, so you see your calculator gives you 0. Okay, so that's the long time value. Okay, all right, that does that problem.